Hello again, everyone. I hope you're doing okay. So we'll proceed from where we left in the previous class. And I think the previous class we did this level, which is byte not, whereby we are able to not, or rather negate each bit of a byte. And we saw that we are going to see how these kinds of circuits are going to be implemented and be used in I think the ALU, arithmetic logic units, to perform mathematical operations and represent other numbers. And we also had adding bytes, whereby we were able to we're given 2 bytes. This is a byte and this is a byte, and we're able to add them together, get the output and the carry. So this is an adder, a byte adder, and yeah, it's an 8-bit adder. And the next one is negative numbers. Yeah, as we can see, it's wired through this. So as we predicted, we're going to use this complement to represent this byte not to represent the negative kind of numbers. And let's see what this level is all about. So the level says, to know the difference between things, you need subtraction. Okay. To get subtraction, first you need negative numbers. Okay. This level introduces 2's complement, the most common representation of negative numbers. Here, the highest digit is negated. For bytes, this means the 8th digit changes its value from 128 to negative 128. You finish this level when you get to level 3 or beyond. So okay, so to represent a negative numbers, this last bit, which is the 8th bit, there's 1, 2, 3, 4, 5, 6, 7, 8. It's negated. So that means the whole number is negative, and this is how we are able to represent the numbers using this. I think it's the most significant bit is 1. That means the whole number is negative. And yeah, so this is the same as the previous one, but representing negative numbers. So let's see. We're told to 1. What is 15 in signed binary? That's okay, timeout. We need to be faster. 1. 15 is 8, 4, 2, 1. Negative 1. This is going to be hard. How do we represent negative 1? Oh, okay. Okay, let's start over again. Okay, was the wrong one. 1 represented by this, 15 represented by 8, negative 1, represented by all this. -2 represented by that. -3 represented by this. What? -14 represented. Oh no. Yeah, this is quite hard. -16. We have to do this and submit. Okay, start again. 1, 15, -1, -2, -3, -7, -12. Oh no. That is just 1, 15, -1, -2, -3. Okay. -13. How do we do -13? 16, 12. This negative. Okay. 8, 16. We need to -3, so that's how you do it. Okay. Let's start over once more. -15, I even forgot how we're supposed to do it. 1, 15, -1, -2, the other way around, -3, -2 again, -15 is, oh no, -7, -6, oh no, -3, oh man. -3, -1, -2, 2 plus 3, Okay, 4. Yeah, let's do this timeless. Yeah, because the timer is messing us up. 1. Let's start over. 1 negative 15 6 8 at 15 -1 -2 to -3, which is 4, and okay, it's a bit confusing. Five and wow, okay, that means that 4 is 3, so let me use 2 and this. Okay, it's like 1 less. 16 is 15, so 8, 12, 13, 14, so this and this, 15. Okay, -4 is -3, so these two, 3. Okay, -3 is 2, -2, that's how you get it. -6 is 5, so 4 and 5. And now I'm at level 3, I can proceed. But let's try using the faster mode and see if we're able to go past this level now that we have a way to find these numbers. So start the race 1, submit. I need a timer. It doesn't have a timer. $15. Okay, 1, submit. 15 is actually 15, submit. -1 is -1, submit. -2 is 1, -3 is 2, -1 is 0, -8 is 4, 3, 8, 7, -7 is minus this, -11 is 8, 4, 2, -11 is 10, so 8, 9, 10, Negative 7 is 6, which is 4, 5, 6. Negative 15 is 14, so that minus that, 14, okay. Minus 19 is 18, which is 16, 17, 18. Minus 16 is 15, which is 8, 4, that and that. Minus 8 is 7, which is that minus that. Good job, not level 3. And it says key takeaways: to go between the negative numbers and positive number, you just flip all the bits and add 1 here. If the highest bit is on, the value is always negative. Okay, but that's different from what I see here. Okay, the byte adder we built also works with signed numbers. As we were saying, the adder that we build can now work with negative numbers. There is still only exactly one way to write each number. Okay. And now we have support for negative numbers, which the way you represent negative numbers you discovered is called 2's complement. So when we talk about 2's complement, we're talking about representation of negative numbers. The next level that we are going to do is, let's do the input selector. So the level says, even though he did not pass our test, we decided to keep the dog. Unlike most Earthlings, he's fluffy and follows simple instructions well. We might want to team you up since you complement each other's shortcomings well. Okay. When the bit selector input is off, output byte A. Otherwise, output byte B. So we are told that if this is the input selector, we have two input bytes, this and this. This is coming from its source, this is coming from its source, and this is the selector. So we are told that if this is off, we would put A. Okay, yeah, you can just have it here. We're told that when the bit selector input is off like this, we output byte A, otherwise we output byte B, and we see the output is here. So for this case, we are dealing with bytes, so we don't need to split it or anything. We just need to kind of switch. So yeah, so we are told that the output here should always be this. Let's see if we get that. Okay. This is not okay, because we are told that when this is off, we should always get this input byte A, and when this is on, we should get this. So it's kind of going to be switching in between these. Okay, so let's have maybe this. No, this is going to enable this, and so if this is on, we output here to this here. Right now we are going to get an issue because they are outputting different values, which is, see, we have the short circuit because these are not outputting the same thing. So we can have another switch, let's say over here, that gets the inverse, of this, and then can power this. So as we can see, we have 0. Let's not use 0, let's use 12 and 67. So if we have this right now, our input is on, our selector selects B, so B is selected, and that's why we have an output of 67. And if it's off, we should get an output of 12, since now this switch is powered. And that's how we are able to select any output that we need. I think this is used in memory to select maybe a memory address or something. So essentially selecting anything from anywhere. This is the circuit that does that, and how we can test it. And everything else. And now this is an 8-bit max. It's a selector. Oh, a max is a multiplexer. That means that it takes a number of inputs. In this case, it takes 2 inputs and outputs 1 input, but we can still select any of the inputs. It's like you have a lot of inputs and you want to reduce the inputs to one physical. We have one physical wire that is the output, but we can use this bit signal to switch in between and chaining these things and making them larger. That means we can essentially build some, like, collapse a lot of inputs into just few outputs, and therefore reducing the communication lines that are required. These are physical wires. And our 8-bit multiplexer, in this case, it toggles between 2 values, and of course it can be larger and support other values, more values. But yeah, so now I think that's enough for our class today, and yeah, I'll catch you in the next one. Bye.